Metsim International. And thank you to Calvin and Inga for getting everybody signed up and joining us today. We will do a Q&A following, so if you could please leave your mics muted until the end, and then we're happy to answer any questions that you have at the end. So jumping right in to talk about the evolution of process models to digital twins, we first should talk a little bit of history of process simulation models. And so going way back, well, maybe not way back, depending on how long you've been around, process simulation really started back in the early 1960s in the oil and gas business. And naturally, that was with the introduction of computers into the world and into the industry. And one important note about that, that's thousands of years after extractive metallurgy. So although we've been able to create quite a bit in 60 years, we haven't quite gotten to the point of encapsulating all of the knowledge that we have developed from the very start of mining and extractive metallurgy. But we are rapidly expanding our calculation methodologies, and what Metsim and many other simulators use these days is called discrete event simulation. And so for those of you who have seen Flowsheet models before, you realize that you have a box representing an equipment, whether that be a pump or a crusher or what it may be, and they are connected to other pieces of equipment throughout the system via streams or flow streams. And an event happens upstream, it has an impact on what comes out of that box and then moves to the next and so forth. And that's a pretty popular way to do things. You get to follow the flow through the system. And speaking of Flowsheet modeling, that has only been available within the last 20 years or so. Again, depending on how long you've been around, you may remember when process simulators were punch cards or even boxes with numbers that you would put in. Now we can actually bring up flow sheets and put the information there, and we'll have some examples moving forward. Several different types of process models. Many of you may be guilty for sending us or people who work with us the model that looks like that there on the left. And that's fine if it gets the job done. But what we're looking for more now these days is something that everybody can use and understand. And that's where our evolution is going to take us. But we'll start with Excel-based models. Everybody has seen these, possibly even created these, and can be extremely powerful in that there are no restrictions on the user. Anything that you can create, you can put into an Excel model. Now, there's not much guidance either, and so you're left creating everything from scratch. Very difficult for others to come in and pick up. Usually the creator of an Excel-based model is the only pilot who can actually get that off the ground. Statistical models. A lot of you might be familiar with GoldSim or Monte Carlo simulation, where you've got a huge database of operational data or weather data, or whatever that may be, and you're going to do statistical modeling to determine trends based on what has happened in the past. Flowsheet modeling, as we talked about, very common these days. It allows engineers and metallurgists to actually view the process with putting in the calculations. And then independent models. There are a lot of brilliant people in this world doing brilliant things, different programming languages, different software, and again, very restrictive in that it's hard for others to come in and pick those up. But they may all provide something useful. And one thing that we're going to talk about with a complete digital twin is you may not have one process model that's simulating your plant. You may actually have several, and they may have a combination of these herein. And we'll talk about how we can get those to communicate. So what is a digital twin? It's a word that a lot of people have used, or a term, excuse me, that we've been throwing around. And just like the picture shows, you have a physical object and you have the digital twin, which is sitting on a server or on a computer or on many servers of computers. And there are few important requirements before you can actually reach digital twin status, if you will. And starting with that, you do need a calibrated, robust process simulation model. So focusing on that first word, calibration. It's a key step. We'll show some examples here. But if you build your process models and they're off by 15 or 20%, you're not exactly creating a digital twin because the error there is too great. So there is a great amount of effort that needs to go in up front by the engineering and metallurgical team to calibrate those process models. Robust is the second word there. It needs to be able to run without error most of the time. And I'm thinking 99+%, to be honest with you. If the software or the model that's in place is finicky or crashes, doesn't always return the results, again, you're not truly getting the benefits of a digital twin because you're constantly waiting for that software to catch up. Then you need a good data management system. That's your second requirement. You need to be able to collect and store information coming from the plant. Not only do you need to collect and store, but you need to cleanse it. We all know that in a plant, instrumentation may vary off from reality, and your data collection and storage should have a cleansing mechanism to be able to remove those bad data points, because garbage in equals garbage out. And your digital twin can be configured to allow minimum and maximums, but we still need to make sure that the information feeding it is cleansed and accurate. Then you need a good import-export system. And again, we'll show some simple examples that we use with our software, but you need data to be able to be exchanged easily among various systems. As we talked about, you may have 3 or 4 different process simulation models comprising your digital twin. You need to make sure that they can communicate in a simple fashion. And then reporting. The point of doing all of this is to be able to get information back out to the people making decisions. And so reporting is something that's often overlooked, especially by us who are engineers building these models. We care more about getting the answers as opposed to getting them to the people that need to get them. A user interface is your next big requirement. It needs to be accessible and usable by operators, by management, by engineering staff. And those interfaces may all look different, but you do need to make sure that they are configured so that each independent person or department within your operation can actually access and utilize. And then finally, trained staff. I may say this 2 or 3 more times. Training is of utmost importance. We need to make sure that the tools that we put in place are used properly. Now let's talk about sort of the evolution here. How do we go from a process model to a digital twin? So step 1 is you need to define your battery limits. If I look at this simple flow sheet here, I've got a copper concentrator, right? We've all seen something similar. Am I going to start my implementation with the entire plant from primary crushing through to the concentrate? Or am I focused at this point on just, say, the flotation area here, or a specific part of the plant? Maybe that part of the plant is more well defined. Maybe you've got more instrumentation, more historical data, and so we're going to start there. You can start small and expand. Again, we can do that within one model or using multiple models. So once your battery limits are defined, you need to then do step 2, which is construct a static or steady state process simulation model. So here's an example of a flow sheet model in Metsim, our software, where we can see we've got just a ball mill circuit in closed loop with a cyclone, and we're showing all the major equipment, the major flow streams, instrumentation, etc. And really what we're after here is a closed mass balance. And so once we get that with the parameters from the equipment and we confirm that our mass balance is close, we start the next step, which is calibrating that model. Again, extremely important here that we spend a lot more time calibrating a model than we intend to. So this is an example of a particle size distribution graph where on the left, the green line represents particle size distribution from a lab or from an assay that we pooled. And on the right is the simulation results for that same stream. So on the left, we have just the one stream in this case, because maybe they took the assay, they did the particle size distribution, but they didn't do any sort of chem scan analysis or detailed assay per screen size. Whereas we can see in the model on the right, we have multiple curves, each color-coded here based on the mineral. You can see on the right, we've got iron, magnesium, calcium, etc. So what we're trying to do when we calibrate Somebody's asking if I could put this in presentation mode. I'd rather not. I have multiple monitors, so I think it should be large enough. It doesn't get too much bigger. But back to what we were discussing here, the goal is to then put these models, so I've superimposed them on top of each other, the two curves. And we can see here in the course, everything down to about 50, 60% passing or so, the courser area aligns very well between the model and actual. But then we see here this green curve is the finds from the assay or the actual data, whereas the model's coming down here. So we need to ask the question when we're calibrating, is that a bad sample, or is the model not treating finds properly? Maybe there are more finds being generated based on the material that's in the mill. Maybe the cyclone is slightly off. But these are the questions that we would want to answer at this step to ensure that we have a well-calibrated model giving us the results that we expect. Once we have our calibrated static model, we need to convert that to a dynamic model, right? Your operation has things changing with time. The model should be able to encapsulate all of those changes. So a few major steps here. We need to set the time step and the calculation lag. What do I mean by that? A process, for example, heat bleaching, we may not simulate every minute or every hour because things are changing on a daily basis. So we may select per day as our time step. Whereas a concentrator, we may look at per minute or per hour, depending on the purpose of your digital twin. The calculation lag, there are two ways we can do digital twins. We can run the simulation models in live time in parallel with the operation, or we can simulate into the future. And again, I've got examples of both of those that we'll look at. You need to set your feed material variations. Everything that's coming in will have variations, whether that be the particle size distribution, the moisture, the head assays. So we need to make sure we have all of those variations built in. Where is their inventory? That's something that a steady state model does not incorporate. Mass in equals mass out. Whereas with an actual operation, you have tanks, you have stockpiles, silos, things that are actually having inventory where material comes in and mixes. And that has a big impact on what happens downstream. So we do need to make sure we assign those where required. You need to expand your control philosophy to meet those changing operational conditions. Those of you familiar with process simulation know that in steady state, you may have what we call a feedback control, where it's searching for the one answer to solve the question. Whereas in a dynamic model, the question changes each iteration. And so you need to calibrate what we would then call a PID control in order to adjust process flows or temperatures, whatever it may be, to answer the question on a changing basis. Then we need to compare the dynamic model results to static model in our operational data. So even though we've calibrated our steady state model, we may lose some of that when we move into our dynamic conversion. So we do want to go back and compare dynamic results. The graph we're looking at here on the right is over 5 years. So this was a heat bleach operation. And you can see in the early days where we're comparing the red, which is the simulated PLS tenor, to the actual in blue. In the early days, the model was quite a bit off, but then as we gathered more information, as the plant became more stable, you can see a very good correlation between simulated and actual. Where the blue line cuts off, that was present day at the time that this model was being generated. But this year into the future, we had a lot of confidence at this plant specifically because we had such good correlation for the previous 3-4 years. We said if we continue on the same plan, and if there are no major changes to our ore coming through being processed, this is the copper tenor that we can expect coming out of the system. Okay. Next step. So now we have our calibrated dynamic model. It's compared very well to our operational results. We need to start defining what information comes in and what information comes out. So now we're taking it from process model to a digital twin. And so we want to say what information feeds the model, okay? And we define these tags. What information does the model need to provide or output? We need to ensure that our models have been configured to provide the outputs to answer the questions that we're asking of it. And in what format is the information shared? right? On the right, you can see an example of just some tag numbers with some units, some values, and a name. We need to make sure that everybody in the operation who will be accessing this understands this structure. Okay. Next step, we need to configure our HMI because we've now got a dynamic model. It's calibrated. It can send information out. It can read information in. We want to configure our HMI and start training our staff. So the first question, are we providing local access or web access? Meaning your digital twin may be installed local to your operation where you're only accessing there on site, or you may have a web access. I'll show you an example with our partners where you're actually accessing your twin on an HTML, for example, on a web address, a URL. And anybody with a cell phone is able to log in and view the information. A next important one, and this one's often overlooked, are staff credentials. You need to have a user and you need to have an administrator. And what do I mean by that? Administrators have the ability to come in and change the brains of your model. So they can actually determine a composition of coal, for example, may have so much sulfur and ash. A user should not have those abilities because if they're not sure exactly what they're changing, that impacts everybody else who will be accessing your system later. So very important that we set up, and it's not just user versus admin. You may have 10 different user levels or staff credential levels, if you will. And it's important that we ensure that the models are not, I'll just say, tinkered with, that are going to then become uncalibrated and unrealistic to our planned performance. We can also then include financial models. So a lot of software these days, Metsim included, has the ability to include OpEx, and that's where the money's coming from. We can follow the money in, we can follow it out, and make decisions based on that. So in this example here, we obviously do not create, as Metsim, we do not create the user interface. I just pulled an example here of a typical SCADA system or something that your operator would typically see. And that's my recommendation, that don't introduce new user interfaces to your users. Put something in front of them that they're used to seeing, and that when they go into the plant then is the same, and you'll create that comfort. Finally, continued maintenance and updates, right? Can't stress that enough. As your plant changes, your twin needs to change. You need to go in and calibrate your process models over again. You need to ensure that, well, we increased pumping capacity. The model needs to be updated alongside of that. So you do need to have, and this goes back to that staff training, you should have either a crew that you're consulting with or an internal set of staff who understand the process models and can implement those changes when changes are made in the operation itself. So when you put all of this together, we can start talking about our partner, ProOpt International. Some of you may have heard of them. Some of you may work for them when I look at the list here on my left. And in the past, the way it's worked is you would take some plant data, you would put it into a model, you would send out some information, and you would make decisions. But what the blue arrow is showing us here is with a digital twin now, we can start making these decisions and actions on the twin and back calculate these things so that we can say what if and how to, right? Those are the two main questions that we're looking to answer here. What if we increase this temperature from 75 degrees to 90 degrees centigrade? What will that impact downstream? What will be the cost implications? What will be the increase in production, etc.? So you can run those decisions at no extra cost and then work backwards to your model. And that's sort of flipping the scope of this operational scheme here. And that's really what we're after. We want to be able to answer those questions readily, easily, and without jeopardizing production and without spending a lot of money. So here's another example of a ProOpt advisor. And what we've got here are inputs. So this may be the engineer or the administrative user of this system, where you can see we've got, instead of having to look at a flow sheet model or an independent model or an Excel-based model where everything is spread over pages, it's spread over different files, it may be very complicated. what we've done here is we've been able to condense all of the major inputs, whether that be, the black mass in the total feed. So we're looking at actual compositions coming in the feed, or it might be a dust feed rate, etc. We may have reagent controls. So we can very easily make these changes here, build our recipe mix and our plant settings, and then come down and click simulate. I think that's something that's easy for everybody to understand and simple to use. And what we can see here is we're quickly able to do 4 cases that I've got shown here. No black mass, 10%, 20%, 30%. So I can actually just change a number, tell it to execute, save the results. Change a number, run it, view the results. And then at the end, what I have are several simulations that have been run with all of the outputs. And I can say, this is the recipe that we need. This is how we're going to operate this plant. And we were able to do that without actually going out into the plant and having to run those things. How do we continue the evolution, right? I started off talking about how thousands of years of extractive metallurgy have yet to be condensed over the last 60 years into process simulation and the capabilities that we have. The first one is autonomous plant control. I have mixed feelings about this one. Maybe I'm a bit old and traditional, but I feel like we're not quite ready to have machines running autonomously, and making decisions in the plant. Maybe I've seen Terminator too many times growing up, but I think we'll get there eventually. I'm not sure that we're there, but you do still, in my opinion, you want some human interaction. We're still capable of making decisions based on human safety, whereas a machine may not yet, but we may get there. Off-site control room locations or single control room for several operations. This is happening a lot already. I visited several in South America myself, where a big company like Vale, for example, in Brazil, may have 6 to 8 operating plants within a 500-kilometer radius. Instead of each one having a control room, they build a central control room in a desirable location. We keep talking about staff and how important it is to train them and maintain them. Well, if you've got them living in a place where their families are, where their kids can play with other kids and go to school, not always the case in a mining town, they're more likely to stay with you for the long haul. So not only are you having the benefit of the decreased cost of building multiple control rooms, but you're also having all of your minds in one place, and you're going to retain them. And that's just great for company development. Implementation of the quote-unquote twin before the plant is built. And you would say, well, isn't this sort of just going backwards? That's just building a process model? And the answer would be yes. However, the idea is we can build and calibrate this twin and have the system ready to go before the plant is built. And we can then configure that for plant startup. Maybe plant shutdown, maybe commissioning. We can start making these plans and build them into our process models and actually start training our personnel, our engineers, our operators before the plant ever turns on. Maybe you cut that commission time from 3 years to 2, and there's a serious benefit in that. And definitely any operation would be happy about that. So that's it for the presentation. I do want to just quickly show some examples. If we look here, so this is an example of Metsim, our software, and I've taken an excerpt out of, I apologize, there was a question here from Graham Marsden. Graham, if you would go ahead, before I jump into this, would you go ahead and unmute and ask that question?
Sure thing. Can you hear me?
Yes, sir.
So I just wanted to check. You mentioned that you could make the digital twin before plant startup and calibrate it. What information would you use to do the calibration if you don't have any real-time data to compare it to?
Okay, very good question. And this is the benefit of doing the same sort of steps and process through at each operation that your company may have. So if you've never done it, you can rely on those that have. And if you have done it, then you may have a data bank. For example, you're buying, a certain ball mill from a certain manufacturer for all of your operations. you may have that level of calibrated information from that other operation on that ball mill. Now, it may not be completely applicable to the material that you're processing now. As we all know, every mine has differences in the ore. But it'll at least be qualitative. It may not be perfectly calibrated on a quantitative level, but again, for training and for pointing you in the direction and your operators in the direction of understanding, that'll certainly get you started. Once then you build up that bank of data from operation through commissioning and into your early years of full production, then you can go back and recalibrate and get something a little more quantitative. So that's been our approach.
Okay, great. Thank you.
Thank you. So back on this, what we're looking at here is just an excerpt from a phosphate model that we've done recently. And we can see again, we've got tanks, pumps, cyclones. So I'm just doing some attrition dewatering here. I then take it through 2 more dewatering stages with cyclones before doing a flotation and creating a phosphate product. Okay, so for this battery limits, we're looking at something that's fairly small, but you can see a great level of instrumentation. We have inventories on our tanks. That's what these streams in here represent. So this is as accurate to a plant that we can get for this situation. So how am I getting information into this model? That's the big question, right? We've seen flow sheet models and process models. I'm not going to go into the details of how we do it, but this is an example, obviously not calibrated for viewing. You could always copy this and put it somewhere else, but we can see tag names and values. And so in my presentation, you can always make this look, let me just get the right, you could always make it look readable, and you could have this report go out to everybody. But when it comes to reading information, we found that text files really are the fastest option. You know, if you're trying to go in and out of Excel may auto-update. It may take a few seconds to do the communication. When it comes to text files, it's just pure data, 1s and 0s coming into the computer. So in this case, I'll just run through the first few tags here quickly, but what we're looking at here is a time unit for simulation. So this is a number of seconds per time step. So I'm looking to simulate this plant every 5 seconds. Maybe the system that we're working on, our PLC, updates every 5 seconds. That's a little optimistic, but just an example here. And I want to simulate 120 minutes. My last question then is, do I want to simulate 120 minutes live time, or do I want to, with a 0 here, I'm telling the program, simulate into the future. So maybe the engineer has pulled this information from the database, created this file, and they're going to say, simulate the next 2 hours because I would like to see what happens if I make this change. So we can come in, and I'll show you how we can run this in silent mode here in a minute, but we can start running this. And what I'm getting now are results back from the model. So the model is simulating just as fast as it can. You can see here every 5 seconds is being simulated in about half a second or less. And I'm getting information on production rates, feed rates, the phosphate in feed, the phosphate in the product, etc. And as this dynamic model is running, right now our text file is fixed. But what if I take this and some other external program wrote into here and wrote that as 315, excuse me. And so something else wrote into our text file. What we can see now, when that increase, it doesn't necessarily jump right up because I have tank inventory. The plant takes some time to respond. And we can actually now, that length of time to respond is something valuable also. We can see now this tank inventory starts going up. So if you have external programs making changes to those text files, the model, even while running, will continue to run. It does not necessarily need to be stopped, data entered, and then started again. So this system is dynamic in that multiple systems may be accessing and changing that information. Okay, I can stop this model. Now, how do we get this to run as a twin, right? We talked about the interface. Operators don't want to look at this interface here. They want to look at something that they've seen before. So I can close Metsim here. And let's reopen this tags in file. And now I'm going to run every 5 seconds. Let's just run 1 minute and I'm going to run this model in live time. And so other systems may be writing into this text file, and then the twin is going to be reading from it, and we're going to run the twin without actually having the program open. And so I've used just a command button here in Excel to demonstrate this. And this is something that we teach our users how to use. This is something that's been around in Metsim for quite some time. But if we look at the code here, it's really quite simple. It's a simple shell command where we say what program is to be run for our digital twin. In this case, it's Metsim. Silent mode is on, and what is the model file? So I'm actually pointing to that model that we were just running. And what happens now is I've got this tags out file, and that would be the standard, but I'm going to tell this now to run the model. And so what's happening is Metsim in the background is now calculating that same model, but I told it to run it in live time. So if the plant were operating and putting out information into the tags in file, the twin is then reading that information, running the simulation, and writing the out files. So we can look at one of these. And now we have different tags that are coming out for those graphs that I was showing, production rates, phosphate amounts, etc. And this model just continues to run until it reaches the number of time steps that I told it to. You can set it up to run nearly indefinitely, or you can set up these limited amounts. You can see that once the command button has been run, I don't even need to keep that open. The system is running it in the background. And so any system capable of reading text files is able to communicate in this fashion. Okay, we should see this get to 13 because I was going to run for 1 minute every 5 seconds. So I have 12 files here because we started on 1, not 0. So now I have record of each 5 seconds that was run. Each of these tag files have different values for these things. I could pull these out, graph them, put them into SQL database, whatever it may be. So that's all I have. I would like to open it up for additional questions or comments from anybody else in the audience. No, if there are no questions, that's fine. I believe everybody has our contact information. We do post on LinkedIn. You can certainly ask us questions there, and and continue the conversation. Okay, there is a question here typed in. I'll read it out loud. I'm uncomfortable with the notion of calibration. Should the process rather be validated? If first principles dynamic simulation is truly following live plant data, which may include erroneous indicators, the simulator ought to be able to correct the erroneous measurements live. How does Metsim do this? So we'll break that up a little bit. The process does need to be validated first. I agree with that. Whether you are engineering a new plant or building a simulation model of an existing, you do need your metallurgical staff. And this goes back to that very initial evolution that I discussed, is we've got thousands of years of operating plants and knowledge in extractive metallurgy. Compared to 60 have not yet encapsulated all of that knowledge. So process validation is the first step. You need qualified metallurgists with experience operating these things. I often use, when I discuss Metsim, I use the analogy of an airplane. An airplane is built to take off, fly, and land incredibly well, unless you put me in the cockpit. I probably wouldn't even know which button to start to fire it up. So despite the fact that you've got this powerful tool and this powerful piece of equipment, you still need a pilot behind it. And this goes back also to my fear of this autonomous plant control. So I agree with you 100%. Process needs to be validated. So you're basing your model, we'll go to the next part of that question. The model's based on first principles. Agreed that that's where you start, right? That's what a process simulator comes with, our first principles. You then start calibrating based on how equipment and material performs. For example, flotation. Flotation is not a simple thing to say, well, if I have so much copper, so much lead, and so much zinc, this is what will be recovered at this particle size. We still need to run those tests because you may take those same parameters on a completely different ore type and they flow completely differently. So that's where the calibration really comes from. The differences in nature that we're dealing with, and then the inherent differences in how equipment operates. Even though it's maybe the same manufacturer and you're operating under the same parameters, it may perform slightly differently at 6,000 meters above sea level as opposed to at sea level. So those factors are part of the calibration. Now we talk about following live plant data, which may include erroneous indicators. This goes back to the importance of data cleansing. We talked here about how data should be cleansed. So you say, how does Metsim correct for erroneous measurements? So I'll take a quick tangent here and describe something that we have called soft sensor. Extremely valuable for very remote operations where, let's say you're measuring the pressure on a hydrocyclone and you know that it should be within, say, 15 and 20 PSI. That's where it's historically operated. And now that pressure starts coming back as 9,000 PSI or 0 PSI. Maybe the instrument went out. What a soft sensor allows you to do is that if the digital twin has been running alongside for enough time, and you do have that quantitative faith behind the digital twin output, then you can actually start using the digital twin reading of what the pressure would be until somebody goes out and calibrates that instrument or swaps it out. And so this is what we call soft sensor, where if that pressure reading is determining something else within the control system, the twin is able to then send in a number, which may be better than, I don't know if it's a default number, if the plant just runs off of default settings, whatever the process may be for operating. So within a digital twin, you do impose limits where a value coming in should be between, I think I said 15 and 20. It has to be within 15 or 20, otherwise the model will throw up a flag. And you can't have then user interfaces available for alarms, information, things that pop up, completely customized. So I hope I answered your question there, breaking it down from top to bottom. Anybody else? Okay, thank you, Mark Kennedy. So it looks like people are starting to sign off, which is fine. We'll hang out until the last. This is not a competition, though. We will cut you off eventually, but I'm happy to answer any questions that you might be typing down at this time. Okay, Nigel.
Yes, hi. Thanks for the presentation. Really good insight on this. So with these digital twins, it looks like you're processing quite a lot of information at single moments. For instance, with your simulation where you had this 5-second interval, how do you manage your data collection? And is there like a historian of some sort that can maybe keep for records in future for, let's say you start recognizing a pattern that's going to happen sometime in the future that may be devastating to your process? Is there some kind of a historian or data storage system that looks at like this whole big data set that you're literally going through at a certain moment? Thanks.
Absolutely, and I think this would be site dependent. And this is our partners in Europe, ProOpt International. This is what they're experts in: storing that information, analyzing the big data, cleansing, and sending information back out. We don't do that within Metsim. We try to keep the model files as small as possible so that they are fast and robust. Right? It's sort of what the Toyota engineers did back in the mid-'80s. They realized that the more moving parts in a motor, the more likely it is to fail. So they started taking parts out. Brilliant. We like to do the same thing with the Metsim model. We don't like to put everything within the the simulation model itself. Otherwise, it's got too many moving parts. It gets big, it gets slow. What we're looking for is fast, robust, accurate calculations. So I would say that, you know, SQL, I know OSI saw, there are so many different programs out there which could store your data, analyze, and provide results, but that's not something that we do at MSI. You can contact, again, our partners at Prompt International. I'm sure they'd have a lot more to discuss with that. So apologies, I don't have more on that for you.
No problem. Thanks for the response. So it literally is just a matter of finding the right connection for your system so that you can get these systems running optimally.
Yes, sir. Yes, sir. That's exactly right. So there's another question here on the chat line. Are there plans to combine Metsim's first principles model with AI applications to create so-called hybrid models? There are a lot of plans to do a lot of things, to be honest with you. The short answer would be yes. I'm not going to go into a ton of detail. We are still developing a lot of those programs internally and hope to have more available in the coming months, and as we learn a bit more and as we push the limits of our software as well as the other programs that we're utilizing. Walter asks us, for the digital twin can incorporate equipment wear. This is part of that calibration that we talked about. So if you have, say, a curve of performance over time, then you can certainly work that into your process simulation model. You know, the model parameters do not need to be set in stone throughout the length of a dynamic model. They can certainly vary with time as well. And so, Walter, to answer your question directly, yes, I've been a part of several projects where we have built in time curves for equipment performance. So yes, you absolutely do want to include those to get the best results from your twin. Okay, we have another question coming in.
If I may, a question revolving my experience with the mine planning area. Often the mine planning and the financial models are built on software on their end, and it's almost like they want to dumb down the metallurgical process to a bunch of fudge factors, as I call them. If we're moving into areas with such capabilities, would you then say actually the mine planning and scheduling needs to enter our system, and then we pop out the financials and the outputs, and it needs to move away from certain areas, typically the planning side, or assuming our models can't feed directly back into their systems. I don't know if that makes sense.
Jonathan, it actually makes perfect sense. And, you know, we could do a whole nother hour. I have a whole other presentation on Metsim and geometallurgy. We won't get into that now, but you can certainly contact any of us to take you through that. But what we've done within the last few years is we've created a mine module within Metsim. So we're not creating the mine plans, but what we can do is read that information in from a mine site or Vulkan or any of these other programs that are used to develop mine block models and mine plans. And we can actually create them within a Metsim process model, which then connects, just like we talked about the discrete event simulation. The mine block model is now your dynamic input to the metallurgical plant. So we can remove the fudge factors and take out the oversimplification, I'll call it, that these softwares are trying to do by condensing the metallurgical plant into 20 parameters. For example, a heap leach. Just because you mine the ore in a heap leach doesn't mean you actually start producing it within that same month. That ore may have been used to build an access road, and it's not going to be ripped and piped and leached for another 8 months. There's no way you can build that type of resolution into your mine block model. Within a Metsim model, we can. And so your digital twin or your Metsim model, your process model, as it may be, can certainly incorporate mind block feed as your dynamic inputs to the model, run through the complete metallurgical plant, and then giving us the process criteria, the costs, the production numbers. So I agree with you 100%. All right, we probably have enough time for one or two quick questions. Okay, on that note, I will say again, thank you everybody for coming in. Thanks for taking the time. There is a comment here. Thanks for showing Metsim additional capabilities which is becoming given. Maybe touching hybrid models will also enlarge the scope of the application. I agree, Raphael. That's part of the next stage of evolution. Maybe I should include that on my last slide here. But thank you again, everybody, for taking this hour. And please do contact any of our team for additional questions and comments. I'll go ahead and end the meeting now. Many thanks again, and take care, everybody. Be safe.